This lecture is going to cover section 4.2 out of the book, Primal Dual Relationships. Last time we saw how to create a primal and a dual, or how to create the dual from the primal. Today we're going to delve into some of the connections between them. So let's start by thinking about the tableau. When we create a tableau for a linear program, we have something that looks like this, where we have our basic variables, which are essentially our slack variables. Sometimes they're just the unique variables to each equation, to each constraint. We have our non-basic variables and the different components of it. When you start out, your basic variables are the ones that appear only once in each equation, or once in the entire thing, one per equation. The tableau under those variables is the identity matrix. Now, we've gone through the simplex method. One thing I didn't emphasize, but is that when you're going through the simplex method, essentially what you're doing in each iteration is the Gauss-Jordan method for solving linear programs, or solving systems of linear equations. So the same thing that you would have learned back in an earlier course for solving systems of linear equations, that's all the simplex method is doing. It's doing those same elementary row operations, just kind of in a more compact form and with some extra rules for determining which way you should go and which variable you should swap in and out. So if you recall, when you are doing the row reductions on an augmented matrix or on a matrix, and you reduce it to the identity matrix, if you perform those same operations on the identity matrix, you will come up with the inverse of your original matrix. That's an important concept that we're doing here that's kind of been hiding in the background. But when we take our tableau, we start out with this identity matrix. Every iteration is just doing a number of elementary row operations on the rows of your tableau. When you get to your optimal tableau, those variables that were originally your basic variables, that originally were your formed an identity matrix, now they are going to give you a matrix. If you take those same columns, they are going to give you a matrix that is an inverse matrix of something you started with. And that's an important concept when you're dealing with duals and trying to understand what is in the tableau and how to read the tableau. To show what's happening here, let's take an example. This is a problem that we saw from earlier in the course. That's our linear program. We change it to add in the slack variables to make them equalities on the constraints. And that leads to our initial tableau, which is what we have on top. After 2 or 3 iterations, we come out with our optimal tableau, which is what we have here on the bottom. In our original tableau, our basic variables are S1, S2, and S3. And notice that in the tableau, they form an identity matrix. Now take those same columns in our optimal tableau, and they form another matrix. This is an inverse matrix of something, and it plays an important role in understanding what's going on. So let's take that matrix out and see what we can do with it. But first off, let's look at the solutions that we have for our linear program, because we're going to use that matrix with some of these things. So I just ran both the primal linear program and the dual linear program through the Excel solver and came out with these answers. So we ended up with an optimal value of 40 for our primal, and you can see our dual has the same thing. The optimal value of our dual is 40. Again, this is emphasizing that one of the main things to know about the primal and the dual is that their optimum values are going to be the same thing. We're going to get into the reasons for that eventually, but for now, just accept that it's the primal and the dual will have the same optimal value. What about our variables? Take our variables in our original, had a value of 5, 5. In our dual, our variable values are 0, 2.5, or 0, 0.25, and 1. And we're going to play with those in a second. So here's the question. If we have solved our linear program, we have our dual, how do we get we know that the optimal value is the same, but how do we get the values of the dual variables? And there's a couple of methods of doing it. Here's the first method. It is looking at the correspondences between our basic variables and our dual variables. And remember that there is a dual variable for every constraint. There is also going to be one basic variable in each of those constraints. So you can do this correspondence that says that this basic variable in my primal corresponds to this dual variable in my dual. If you want to get the value of the dual variables, first off, take your original values of your basic variables and find what they are in the final tableau. So if you look in the final tableau of the problem we just had, the values of S1, S2, and S3 are 0, 0.25, and 1. You can also get those from the Excel solver. So those are the values of our basic variables at the optimum point. Add in the original coefficients. In this case, they are all 0. They won't always be all 0 because you can get a basic variable that is in your original optimum equation. Add them together. That will give you the values of your dual variables. Now, this is highlighting something that is important. Remember that those dual variables, in many cases, they're your slack variables. They're your slack variables in your constraints. Each of the dual variables are related to each of those equations, to one of those equations. The values of the slack variables are related to whether or not that constraint is binding in your original problem. And if it's non-zero, if it's non-binding, it tells you kind of how far away your optimum value is from that line. That is very closely related to the values of those dual variables. This is something we're going to look at a little bit more closely in later points, but just kind of try to understand the concept here that the slack variables or the basic variables, their values are very closely related to what your dual variable values are. Second method for the values of the dual coefficients, and this is using that inverse matrix that I talked about. So this was our original linear program. We solved it out. We put in the tableau. We solved the tableau. We ended up with this as our optimal tableau. And we said, take a look at our original basic variables, see what their values are now in the tableau. That gives us a matrix, and we call that an inverse matrix. What can we do with that? Well, we can use that matrix to convert our original values into, or to use our original values to get our dual variable values at the optimum point. So note that S1 and S2 and S3 were our original basic variables. We use those to get our inverse matrix. But after 2 iterations, they aren't our basic variables anymore. We have different basic variables. What are the new basic variables? X1, X2, and S1. Those are our optimal basic variables. They form an identity matrix as well, but you have to rearrange them a little bit. So if you put S1 followed by X1 followed by X2, those columns give you an identity matrix. So here's where I have them in order. Go back to the original tableau. What were the initial values of those variables in your objective function? They were 0, 3, and 5. S1 wasn't in there. Our original objective function was 3x1 plus 5x2. So now we have a row vector that represents the original values of my new basic variables. Take that, multiply it by my inverse matrix. What do I get? I get 0, 2.5, and 1. If you remember, that is the value of my new dual variables. That was the value of y1, y2, and y3 at the optimal point. So hopefully after seeing this, you're starting to get a bit of a sense that this mysterious dual linear program the results to it are very closely related to the results of my original primal program. We're going to delve into this a little bit more later. But this inverse matrix is essentially giving us a way of translating from our original primal problem into the solution of our dual problem. Now here is one of the fundamental theorems when we're talking about duality. It's put in terms of maximum problems and minimum problems. So I talked about I started off by talking about the standard maximum problem as the primal problem, where you are maximizing things, all of the constraints are less than or equal to, and all of the variables are non-negative. That's a standard maximum problem. When we have a linear program that's in that form, the dual is a standard minimum problem. So you're minimizing something. Take any feasible point from your primal, call it P. Any point, not the optimal, not necessarily the optimal, any feasible point. Do the same with your dual. Take any feasible point from your dual. This theorem says that the value of your objective function in the primal at that feasible point is always going to be less than or equal to the value of the dual at the feasible point from the dual that you selected. Doesn't matter what the points are. The primal, when it's in standard maximum form, is always going to be less than or equal to any point in the dual. And the only time they overlap is when you are at your optimum point. Okay? So this theorem is basically, in a sense, saying that these two problems don't overlap. Your standard minimum is always going to be higher than your standard maximum. They're only going to overlap at one single place, and that is where the optimum is achieved. This is a theorem that we're going to use to show some of the results about duals. Now, just a little bit more about that we're going to get into about using this inverse matrix. So again, this is the same problem. We had our original matrix that was an identity matrix. Through the iterations, we've turned it into this new matrix, which is, we've been calling an inverse matrix. Well, take a look at what we've done. What we've done, as I said, what we're doing here is Gauss-Jordan method, what you've seen in solving systems of linear equations by using matrices. And if you recall, when you're doing that, you take an augmented matrix, you augment it with the identity, you row reduce until the left-hand side of that augmented matrix is the identity matrix. What you have on the right-hand side is the inverse of what you started with. Well, what we've done at our terminal point of our objective function, and in fact at any point, at any iteration, we have embedded in this tableau another identity matrix. We have, in this case, if that's column 1, column 2, and column 3, we have embedded an identity matrix in here. We go back and look at our original. That is giving us that matrix. So if you take that matrix from our original, putting it in the right order, so S1 first, X2 first, and X1 second, and X2 third, because that was the order that we have of the identity in our final tableau. Multiply it by this inverse matrix. What are you going to come out with? You multiply those, you will get the identity matrix. So I've been calling it the inverse matrix for this reason. It is the inverse of some of the columns in your original tableau. What we have done is we have hidden in this tableau an augmented matrix for where we're trying to find an inverse. When we've thrown on top of that a bunch of rules for saying, do this operation, do this operation next, and stop when you get these certain conditions. But at any step along the way, you will have an identity matrix sitting in your tableau. Go back to your original columns. It will be the inverse of the columns in your original matrix. What you are doing is row reductions, where at any point you can multiply these things together and get the identity. This takes a little bit to get your head around, but that's what the identity matrix is in there. Note that any column in the optimal iteration is equal to the inverse matrix multiplied by the original tableau. So even if you take one of your other columns, so if I were to take the S3 column, multiply it by this inverse, I am going to get what I originally started with for that column. So there's a very close relationship. You're essentially hiding row operations inside your tableau as you solve for this, and it's related to the dual. Okay, so that's kind of an overview. I've given you a bunch of stuff to think about and relationships that are within this matrix that you can play around with a little bit. We are later on going to go into some proofs of this, a little bit more than what's in the book, but for now this should give you a good overview of some of the relationships that are hiding in there and some of the relationships between the primal and the dual.